Hi everyone, welcome to the lab session 1 on microprocessing and interfacing. My name is Anubhav Elens. I am a research scholar, a PhD student under Dr. Vinay Chamola, and I'll be guiding you through your lab sessions. So let's get started. Just a quick intro of what I research on. So I work on applications of AI and blockchain in public sector areas like healthcare and real estate. So this is my intro of who I am precisely, and let's just get started. So let me start sharing my screen. All right. So what is DOSBox? So DOSBox is a free and open source emulator program that allows you to run MS-DOS applications on modern operating systems. So it creates a virtual environment that simulates the behavior of a IBM PC. Like IBM PCs were the first kind of PCs which incorporated the x86 architecture, and those computers ran MS-DOS. So the DOS box allows you to run old DOS-based softwares and games that may not be compatible with the newer operating systems. Also, DOSBox emulates the CPU, memory, and other hardware components of an IBM PC, including the 8086 processor. So it also emulates, you can see here, um, just a second, let me take out the pen. All right. So it also simulates the BIOS and other firmware that is present on a real PC. The importance of the word emulate, we'll be discussing about this later. So this allows it to run software that was written for the 8086 processor and the MS-DOS operating system on a newer modern operating system. All right. So many of you in your childhood uh, must have played this game, Wolfstein. I had played it, and even I talked to Dr. Vinay Chamola. He also revealed that he also played this game as a childhood. So this was completely based on the MS-DOS application, and you'll get a glimpse of how to make such a game, how to make things interactive in the towards the later sessions of the lab. We won't be obviously making this whole game; it's too complicated given the scope. But at least you'll have an idea that how such a game can be made. Maybe you can if you want, you can code such game yourself. So the program is configurable, allowing the user to change various settings such as CPU cycles, sound, graphics, and even network support. So we won't be delving into all these aspects. We'll be keeping things very simple. And just let in summary, DOSBox is a powerful emulator that allows you to run old MS-DOS software and games on modern operating systems by emulating the hardware and firmware of an IBM PC compatible computer, including the 8086 processor, which will be the focal point in our discussions. All right. So next thing which we have to discuss is what is MASM. So MASM stands for Microsoft Macro Assembler. So it is an x86 assembly language compiler and development environment developed by Microsoft for their operating systems. So and it was first released in the early 1980s for the 8086 and the 8088 processor architecture families. And since then it has been released for many other processors up till Pentium. So MASM provides a set of macro instructions that can be used to simplify the assembly language programming and improve the code readability. So let's not just, you can see the slide once, let's not go too much into the theory of what it is. Let's try to understand in practice that what is MASM in practice. So let's just read the last part of it, that in summary, MASM is an x86 assembly language compiler and development environment developed by Microsoft for their operating systems that provides a set of macro instructions and powerful debugging and development tools for assembly language programming. All right. So what is now comes in still a little more theory. So let's begin with what is Debugx. So Debug X supplied by MS-DOS is a program that traces the 8086 instructions. And using debug, you can easily enter 8086 machine code program into memory and save it. So, excuse me. So 86 machine program into memory machine code. So if you notice that what we write, like you might be writing some instructions like move ax comma bx, but what it actually means is set of some instruction, some set of byte codes, machine codes, like you can see here, or you can see here, or you can see somewhere here. So Debugx does that for you. It traces the 8086 instructions, and you can easily convert them into the machine code using them, and can also execute that using Debugx. So debug can be used to test and debug the 8086 and 8088 programs. The features include examining the changing memories, the register contents, and believe me, um, this is exactly what we'll be doing throughout our lab sessions. We'll be writing some code, going and checking the register values, seeing what changes it has done, going to the specific memory locations. In fact, this is what all the programming is all about. It's nothing very complicated. It's just a, as I always say, it's just a set of few um, definitions, like x is equal to 56, or some definitions, some defining of the variables, and some flow control, which means your if else statements, your for loops, your while loops, and that is it precisely what your any coding languages. Just some definitions, and equalizing, like making some equalizers, and then having some flow control based on that. We're again going back and updating those. So all right, so let's begin first of all by installing DOSBox and Debugx. So you might be receiving the PDF of the PPT which I'm showing here, and click on the link to the DOSBox installer. Click on the link to MASM and click on the link to Debug and Debugx. I've already downloaded all of these, and I'll just show you my downloads folder. So these three files you'll get. Double click on this. So once you've done this, these 5 steps you have to follow. On the just install the DOSBox to the default memory location where it tells you to. Extract the MASM folder by right clicking and WinRAR extract here. So once you click on extract here, you will, where did I extract it? Is it gone? So you will find this MASM 611 folder. Just copy the entire folder, and just copy this into the D any file. I have copied it to my D drive. So here I've placed that, and inside that there'll be a bin folder. So the third thing which you see here, the third link, debug and debugx, extract that, and whatever files you see inside that folder, you have to paste it inside the bin folder. Once you've done that, on your desktop screen, you'll see the DOSBox already installed. So open the DOSBox by clicking there, and this is how it will begin. Like, all right. So once you've reached this step, take a pause, take a break, because next what we're going to do is start Debugx, and we'll execute few simple commands in that. So if you wish, you can pause the video now. All right. So I hope you're back now, and so once you've installed the software, follow these sets of 5 instructions. Now this is very important for your every lab session, because you have to do this practically right from your lab session 1 to whatever labs you have, and then in your lab test also you'll have to do. So don't expect any help from the lab instructors in the starting. Obviously you can expect some help, but in the lab test, don't expect us to begin the Debugx for you. I see that many people are just, they came prepared with all the codes and everything, but they do not know how to launch the Debugx. So don't let that happen to you. So here are the set of 5 instructions which we see, and first step is to mount the D drive this way. All right. So let me open that and type it right in front of you. So mount D backslash masm 611 slash bin. After that, I'll change to the D drive and excuse me, um, Debugx. All right, so we're inside the Debugx right now, and a quick way to check if this is working is just see the register contents of it right now. So everything must be pointing to 0, and the data segment ES, SS, CS all are pointing to 859. Okay, so if you've reached till this point, good. Now let's just before starting to code, let's just see the few debugx basic conventions. So debugx is not case sensitive, so anytime I type capital mov and you type small mov, it does not matter. In fact, not just in instructions, even in the name of registers and anything, it's not case sensitive. Debugx recognizes only hexadecimal numbers without a trailing edge by default, so 11 is interpreted as 17 and not 11. Very important. Debugx displays a list of commands and their parameters by entering a question mark at the command prompt. So you can try that right now. Um, just go through them. The basic instructions are all written here. So this will help you understand the format. And if you forget sometime like what was the command, so you can anytime come type question mark and see this. All right. So next is debugx displays a list of commands and their okay, this we've done. Segment and offset are specified as segment colon offset. So by the time you might be seeing this video, this must have already been covered in the lecture series lecture section. So if you're still confused about this, I would highly recommend you to revisit that. Spaces in commands are only used to indicate separate parameters. Okay, so this we'll see as we're going ahead. Just for those who are a little confused, segment and offset thing. um, So the DS is your segment, and right now if it is 859, then whatever your offset will be, offset can be defined either in your register or through memory or through register memory or through immediate value. So whatever be, let's say a value of offset, let's say it's 100. So the 8590 is the segment, and at the 100th offset from that point, after multiplying it by 10, would be the exact memory location in the whole space. All right, so for this I would recommend that you go to you revisit your your lecture class. All right, so now is the time to so there actually I thought that there are multiple approaches to take take this session from this point onwards. So I thought that why not let's just first execute, learn, and then come back to what each of these commands are doing, so that you already by the it's not very difficult actually to understand. So I'll just give you a glimpse of the command syntax and their description. Okay, so let's begin the follow along exercise. So let's first view the contents of the register. So this we have already done just now. Let's do it again. R and enter. So here you see the AX, BX, CX, DX, all the registers, even the flag registers are here. What each of these flag registers are, you'll come to know as we progress along. So now let's write a simple program to add two numbers. So the first thing to do is is type the A command, and that will open the window for you to type the command. So move AX comma 01 and move to BX value 02, and then simply add AX and BX and store the result back to AX. So this is what this instruction means. All right. So now let's view where the instructions got stored in the memory. So for that, we use the U command. And here you can see the top three lines. Here is the command, the unassembled command. So when you type this command, what it actually got stored was in this format B80100. How many bytes can you see? 3 bytes, right? 1 byte, second byte, third byte. So This uses 3 bytes to store the data, and therefore the next instruction where it is getting stored is 100 plus an offset of 3. So at the 103rd location, you'll see the next instruction, which again takes 3 bytes of data. So the next instruction would come at 106, and now the add instruction ax comma bx takes 2 bytes. So therefore, from the 108th offset is all the random commands, like, not given by us, but basically up till here we want to execute things. Okay. So before we execute the command, let's see where the instruction IP is pointing to right now. So initially IP was at 0100, and the next command you can see here is written as RAT. Now if I type R, so since I've put a valid instruction into the memory, it is showing move AX comma 0001 here, right? So, and the instruction pointer is again pointing to 0100, but here the important thing is that as we execute, the IP will also change, and the next instruction which is going to be executed will also change. So let's execute the first command by typing T. So at AX, we see that the value got changed from all zeros to 0001. So observe now where the IP is pointing to. Similarly, let's do it 2 more times. So IP right now is pointing to 103. That is the next instruction. So let's do it. Let's do it 2 more times. T and finally T. So here the BX value, BX register got this value, and then finally the add AX comma BX added these two numbers together and stored the result back in 03. So that is a very simple thing which we did, adding two numbers. Now let's view where the instructions got stored in the memory. So it's another follow. Sorry. Now let's do another follow exercise, and this time let's just view the contents of the register before we begin. Sorry. Okay. All right. Before we attempt the next exercise, uh, right. This is in the slide. Sorry, I got a little messed up. Another follow along example. So now let's try to see the contents of the random memory locations. Big To see the content of the memory, we have to use the D command and the display command, and the range of memory which we want to see, we can just specify it in the same segment colon offset format. So let's see this 859 colon 0200. Uh, as obvious, it will be all zeros because nothing has been put here, just a complete refreshed memory. So nothing is here, nothing of much value. So let's try another one, and this time ds colon 100. Oh, so we see something, right? And does it look familiar? Yes, of course, yes, it looks familiar. And what it is, so this is exactly the byte equivalent code of the ALP which we wrote originally. All right, so you can compare here what we're seeing here, B80100, so B80100 and BB. So you can just simply compare, and it's stored in the little Indian format. So things are making sense. So isn't this amazing to note that instructions also lie in the same segment as our data does and can be read, copied, executed. So uh, it's actually, we'll come to a few of the important things that instructions we cannot fiddle with just like that. So let's take an example and see how we can uh, where things can go wrong. So for doing that, let's store this DEAD at memory location DS155H. So there are many four-digit words or four alphanumeric words like dead, beef, and all these things, which are sometimes used to, um, make sense because they are in the hex format also. They are available. So let's try to store dead at memory location 155H, and I highly recommend that you pause the video and give it a try because it's very simple based on the exercise which we just did. So pause the video. All right, let's store let's store that now. So without looking at the solution if we have to do. So what we'll do is, first of all, again go back to the assembler, which where we'll write our instructions, and this time note that where it began from, 108. If you notice in the solution, what I've done is that you can specify the where you want exactly your instruction to be written, like ADS colon 108. That would also result in the same thing. All right. So first, what we have to do is move to the BX register the value DEAD. All right. Once you've done that, now at the memory location 155, you can copy the contents of the register B, and that is it. Let's just see through the U command, and you can see that this command, the byte equivalent would be BB ADDE. ADDE is dead stored in the little endian format. The next, what we can do is just review the contents of the register once, and you can see that the next register, next instruction which is to be executed is BX comma DAD. So let's execute this by typing. Before we execute, we should ideally see the contents of this memory location 155, and you can see that there is nothing as of now here. All right, and after I execute T, and then let's see the D S 155. Uh, it's good. Oh, sorry. The next. So now only BX. BX has the dead stored inside it. I have to execute T one more time, and then if I execute D, if I just simply enter D also, um, I have to specify DS. Let's see it from this itself, from 100 onwards. So this is where our instructions have got stored, and at the 150, at this offset, you can see AD stored. So in the little endian format, the AD, which is the lower byte, gets stored first, and DE, which is the higher byte, gets stored afterwards. So many of you, will feel confusion. In fact, when I was doing my undergraduation, I felt the same. And an easy way to actually decode, so I'll draw it here actually for your easier understanding. That, let me take out the pen. So these memory locations is flowing in this direction, correct? And what we are used to seeing memory locations is something in this direction. So I'll just draw a table of these memory locations, and I'll try to fill up some of them for you. So the memory by default, if not specified otherwise, will be byte organized. So what I'm telling you trick is something which has helped me understand, clarify my MUP concepts to a great extent. If you just understand the memory organization, that how memory, a byte organized memory is organized. So, and if you can just draw this picture in your mind, then things will become very clear for you. All right. So here we have the location. Oops. 8590 offset 100. Let's draw 100. So up till some few dot, you can just go on 101, 102, 103, and from here you can keep on picking up the values and filling it here. B8, 01, 00, BB, and this way you can keep on coming down till the 150th, and here you can put 00. Finally at 155 you will find AD, and at 156 you will find DE. All right. So it's important that although it's not making much sense in this problem, but when we attempt future problems, you'll start seeing that this sort of a memory organization in your mind helps to clarify the concepts to a great extent. Okay, so finally let's just attempt another problem. So I won't type this, it's very simple. Let's copy the content of memory location back to one of the registers, the CX register. So this time again we'll type the A command, move CX 155, and let's just review the contents of the register before copying that. So you know that instruction pointer, the next instruction to be executed is CX 155, and after executing that through the T command, the CX register is filled with the value coming from the memory location 155, all right, which is dead. So there'll be 10 offenses against the MASM compiler. And if you commit any of these 10 offenses, no matter how well you've coded in the past, immediately your program will start to behave abnormally and you'll have no idea why is it happening. So until you rectify your mistake and say sorry to the MASM compiler, you won't be forgiven. So first offense is that thou shalt never attempt to manually change the contents of segments using Debugx or fiddle with the data segment where the instructions are written. Read it carefully. So thou shalt never attempt to manually change the contents of segments using Debugx or fiddle with the data segment where the instructions are written. Don't try to do that. Don't try to manually, since just now you've learned how to go to a particular memory location and put your data there. You might feel, okay, let me just do it in the instruction folder in the contents of the segment. Let me try to manually change them. But as soon as you do that, the whole thing collapses and the program will start to behave very abnormally. So follow the standard pattern, and the later offenses which will be covered later on. So if you just follow these, if you just keep in mind these 10 principles, then your program will execute for sure. So here are the debugx commands which we have used till now. A stands for the assemble command. The syntax is A, pointing to the address where you want. Just pause the video and give it a read if you want to. The D, the dump command. I spoke earlier the display. Sorry, it's the dump, but it does not matter. Like you can see the contents of the 128 byte block of memory starting at the CSIP if a target program is loaded. The syntax for the same is D and specifying the range. Then R command for register. So here you can specify if you want to look at a particular register. Let's say that now here I am and I want to, here is the IP value 010F. So if I just want the IP value, so I can specify R IP. So I'll only see the value of the IP. And if I want, I can actually take it back to 100. So here you can see that it is again pointing to 100, and the next instruction which is showing it to be executed is 0001. So you can start executing your program from the start by manually changing the IP. The trace command, as we have used, is used to execute the instruction present at the CS colon IP. And the syntax for this is just type the T, and if you want to execute particular number of instructions, just specify those instructions after a space. And you can also specify the address from where you want to execute the instructions. So the tasks to be completed, you might get another hint, or the TAs will help you in attempting this. So you've read this addressing modes, the immediate addressing mode, the register addressing mode, the register indirect addressing mode. And using this, you have to move the value 1133. Now, you have to figure out whether this is in the decimal or in the hexadecimal we're telling you into the register AX. Swap the lower and the higher bytes in AX and move them into BX. All right, and move the value in BX to the memory location at an offset of 20 from BX. So this should be simple and straightforward based on the exercises which we have done right now. The second problem is move the first letter of your name ASCII character to the location specified by this. And finally, the third problem statement is fill 32 decimal bytes of extra segment with ASCII characters for the first two letters of your name, like AB, 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 or whatever your name is for me, AE, AE, AE. Okay, so give it a try. The problems, the tasks are definitely kept a little higher so that it's not just, you get to use your gray cells, your brain cells little bit. And obviously TAs will be there to help you, the research scholars and your lab assistants will be there to help you. So that is it from this session. Thank you. See you next week. Bye bye.